Thank you for the introduction. Um, so yeah, this is my first time attending A-Life, and I've really enjoyed all the talks so far. They're very inspiring. Uh, and I hope that this can be interesting to you all as well. So this is joint work between myself and Khulud, who's online. Hi, Khulud, if you're there. And our work is essentially trying to evolve a culture in a robot swarm and I guess subcultures as well. Yeah, so I'm sure many of you are familiar with the swarm paradigm. Swarms are supposed to be distributed. Traditionally, they're also homogeneous. And we usually take a lot of inspiration from both, well, biology and nature in order to design um, uh, for, I guess, swarm behaviors to solve particular problems. So here I think these are fire ants self-assembling to build a bridge across two leaves. And here we've got a self-assembling modular robot system. So what we're actually interested in is taking inspiration from human culture, human society, because I think we've all seen that in different cultures, we have different kinds of social codes, different social norms. And so if we have a kind of heterogeneous swarm, in this case, this was the Swarmanoid project, where we had individual robots with different capabilities, which could be both physical or behavioral difference. But yeah, I guess the idea is how can we kind of develop or evolve a culture to help the robots in that swarm to better coordinate. And then this picture at the end here, I think it's, I can't remember what the robot's called, but it's a delivery robot and it's gotten stuck on a curb. So if robots are operating in a human environment, what I guess there's a question of how we can kind of design social norms to aid that human robot interaction or human swarm interaction. So how can we actually evolve this swarm culture? So we've actually kind of based our work on cultural algorithms introduced by Reynolds RG, not the Reynolds who created the flocking algorithms, a different Reynolds, and also Franklin and Bergerman. And so we've got, for our version of the cultural algorithm, we've got several ingredients. Firstly, we have a belief space where each robot is associated with its own individual belief space. And you could say that the contents of all the belief spaces together represent the swarm culture. And so when the robots move around, they're able to interact with each other and also influence each other's belief spaces. And there's also an update mechanism where the robot updates its own behavior based on the contents of its own belief space. Great. So in this way, we're hoping that we can evolve the culture over generations. So I guess we've been kind of exploring different use cases for this. And in our particular use case, we were thinking about emergent morphology in the swarm. And so here we've got behavior parameters, and this is taken from Reynolds blocking algorithms. And it's also inspired by Hiroki Sawayama's work in swarm chemistry, because we're kind of interested in how different subgroups within the swarm might be able to create distinct morphologies, basically, as you can see in the pictures on the right here. So yeah, we've got three different parameters: cohesion, alignment, separation. And in particular, for our cultural evolution method, we've got two parameters: influence and resistance. So influence is where robots, that parameter determines how influential each robot is in influencing the other robots in the swarm. And resistance determines how resistant the robot is to the updating mechanism. So they want to keep their behavior, basically. And so in our use case, we're going to look at how to dial the diversity in the swarm culture, either up or down. Cool. So these are very preliminary results. We were just trying some things to see what would happen. And on the top row, we're looking at diversification. So at the first time step, we've got just two subcultures. Oh, and also on the axes, we've got the different behavioral parameters, which are cohesion, alignment, separation. And you can see that after 100 iterations, we've actually been able to diversify it. So we have a few more subcultures on that plot. And then on the second row, we've got coalition. So we're at the first time step, we're starting with a big spread of subcultures. And after 100 iterations, we just have that small blob in the corner. Okay, so why might we want more or less diversity in the swarm? Well, we're kind of inspired by our own work in our PhDs. So Khulud, she works on imitation learning, where she's trying to learn the individual robot behaviors from the global view, from video demonstrations of the swarm. And so in this case, if you have less diversity, if you have robot controllers that are more similar to each other, it might be easier to do this imitation learning. And for me, I'm looking at fault detection and mitigation in the swarm, and I'm learning from the local perspective of the robot. So if you have more diversity in the behaviors of the robots, this might give you better tools to mitigate for different faults. So that was a pretty quick run through of ideas. As I said, it's very preliminary work, but in summary, we've been trying to evolve the kind of culture or the subcultures in the swarm, in a robot swarm. And yeah, so there's a few ideas or questions that we still have. For example, can we develop an objective function towards, I guess, different applications or solving different problems? What other use cases might there be for this approach? Also, what kind of similarities are there to consensus or opinion dynamics? And how might we represent these swarm behavioral rules or the social norms? So yeah, feel free to get in touch if you want to discuss more, and yeah, open to questions.